Okay, anyway, this section, we got a couple new definitions for acids and bases. We had the Arrhenius acid base. Now we're going to add in the Bronsted-Lowry version plus the Lewis acid base definitions. They're different because there are actually different contexts for acids and bases. There's different kinds of reactions that can happen. So that first go around, Arrhenius acids contribute to that hydrogen ion in solution. That's what defined an acid. And the Arrhenius base led to hydroxide ion in solution. One or the other, one's an acid, one's a base. These definitions are slightly different, and they're for different contexts. So Bronsted-Lowry acids are proton donors. I understand that a proton is a hydrogen ion, and so Arrhenius acids are Bronsted-Lowry acids. But the difference between this and the other version that we talked about is that if I have an acid in this context, like hydrochloric acid, I don't actually need water for these reactions to occur. I just need to have one thing to accept a proton and one thing to donate that proton. So this hydrochloric acid can react with ammonia to make some products, right? This is going to donate a proton, donate this hydrogen ion from here to this molecule over here. And if this gains a hydrogen, what does it become? Ammonia. That has that positive charge. But then there'd be this chloride ion left behind, so I end up with an ionic compound over here, ammonium chloride, and I can do this without water being present. This didn't contribute to hydrogen ion in solution. So this is not really an Arrhenius acid in this context, it's just a Bronsted-Lowry acid, because it donated a proton to that ammonium. Right? But if I had it from that last section, and I reacted that with water, and it donated the proton to the water, then it is an Arrhenius acid. Right? Because I still get the hydronium ion. I'd still have that chloride ion separately. Right? So this was from that last section. Hydrochloric acid obviously can act as an Arrhenius acid, but if it's reacting with ammonium and there's no water and you make that ammonium chloride, it's not technically an Arrhenius acid, it's just a Bronsted-Lowry acid, which is why they had to have different definitions to begin with, because sometimes it is one thing without being the other. So they had to come up with another definition to explain this kind of reaction between hydrochloric acid and ammonium that didn't apply before. All right. Then I can look at this reaction in context. What did I get yesterday when I combined ammonia and water? Ammonium and hydroxide. Pen stopped working. Heck. But if you look at this in context of Bronsted-Lowry acid, that definition, what thing, the water or the ammonium, donated a proton? The water did. So the water is an acid in this context. It's a Bronsted-Lowry acid. So hydrochloric acid, right, was a Bronsted-Lowry acid in these two first definitions, or these first two equations that I did, sorry. But that second equation, it can also be considered an Arrhenius acid because it led to hydrogen ion or that hydronium ion in solution. The first one, there was no water, so it's not technically an areneous acid. Down here, the water can act as an acid when it's reacting with that base, ammonium. And we're gonna see that when we're talking about Bronsted-Lowry acids. If you're gonna donate a proton, something else is gonna have to accept a proton. So you'll see that for all of these examples. This is the acid, this is the base. Up here, this ammonium is acting as a base, just like down here. Right? This water here is acting as a base when it accepts a hydrogen ion from the hydrochloric acid. So you always have acid-base pairs for this definition. There has to be a base to go with the acid. Something has to accept the proton while the other thing donates. So you should see something there that we've talked about before, right? Is water an acid or a base?
Yes.
It's both, right? So it's not one or the other. It actually acts as both, and that's the whole point of acid and base properties to begin with. That only occurs with water, right? You can only have an acid when it's in water or base when it's in water, except for up here, right? These didn't need water to react. So there are exceptions, but the whole concept came from water because in aqueous solutions, you end up with that corrosive acid, even that corrosive base. So that's where it originated from. Water is an acid and a base, can be both. A Bronsted-Lowry base is the opposite of an acid. It accepts the proton instead of donating it. So in that last definition, I gave you 3 examples of Bronsted-Lowry acid-base reactions. Again, just to emphasize that, a base is anything that accepts a proton, so these 3 things were bases, according to that Bronsted-Lowry definition. And the acid is the thing that donates, so these 3 things were acids. As you have examples of acids and bases, we don't need to necessarily put another one in here, but I do want to put the exception in here, the thing that does not apply. Right? Sodium hydroxide is not a Bronsted-Lowry base, but why not? When you put this thing in water, all it does is ionize. And it does lead to that hydroxide ion in solution, which is the whole reason why it would have been considered an areneous base. But did anything in that process accept a proton? No. In reality, I could actually circuitously talk about how that hydroxide could then accept a proton from something like water. But when it does, it becomes what? If it accepted a proton from water, what would it become? It'd become water, and the water would become hydroxide. So in all reality, you'd be just chasing your own tail. It doesn't really matter that that happened, right? So technically, the hydroxide itself could maybe be a Bronsted-Lowry base, but sodium hydroxide is not a Bronsted-Lowry base because it doesn't accept a proton. So those ionic compounds that contain hydroxide are not Bronsted-Lowry bases. They are bases according to that Arrhenius definition, but they are not bases in this definition. Only things like ammonia or water itself that can accept protons would be considered bases under this definition. You guys kind of catch what's going on then? You see why there's 2 different definitions, because they're different scenarios. Technically, like I said, this could be considered a Bronsted-Lowry base, the hydroxide, but then you kind of chase your tail because you end up with the exact same things over here that will react again to remake these 2 things. Right? Really confusing. Back and forth. And nothing really changed. But the sodium hydroxide itself is not considered a Bronsted-Lowry base because it cannot accept a proton. This thing does not accept a proton. It just ionizes to make that hydroxide ion in solution. Whereas this ammonium here that's a Bronsted-Lowry base is also an Arrhenius base because it leads to hydroxide ion in solution. So it can be both. Right? Water in this context right here, acting as a base, is not an Arrhenius base, because did I make hydroxide over here? No. So it really just depends on the context, on the example. If it accepted a proton, it is a Bronsted-Lowry base, but that does not necessarily make it an Arrhenius base. But it might be both. Who knows? So it's always just dependent on context. And you guys will figure that out as we go. Right, again, Bronsted-Lowry acid-base reactions, protons are transferred from one reactant to the other. So one thing's an acid, the other thing's a base. If something accepts a proton, it's a base. If it donates a proton, it's an acid. So, I mean, I could put another example in here, but you kind of get the idea anyway, I'm guessing. Right? We should put another example in here just in case, though, right? If I have that acid, whoa, that's not what I did. Don't even know what was going on there. I was just trying to put a plus sign. And I have this thing acting as a base. I'm trying to decide if I want to make this complicated or easy. Complicated? Yeah, that would make more sense. It's going to donate a proton. This acid is going to donate a proton. This base is going to accept one. What do I make for a product? And hydrogen sulfate. If I had enough of this base, though, you should understand that I could actually accept all the protons from this acid, and I actually could react this completely and end up with, ammonium sulfate, but then I'd need 2 ammoniums per sulfate to make it balance. Right? It kind of depends on the context. Right? If I only had so much of this, if I had an equal amount of each, I'd end up with this product. But if I had double that compared to this, I could actually react completely and end up with the ammonium sulfate as a product. So this is an acid because it can donate a proton, but you should see that it can actually donate 2 protons, right? So it depends on how much of that base do you have. Would you make the bisulfate, the hydrogen sulfate, or would you make the sulfate at the end? Right, so if I gave you 1-to-1, you'd probably only be able to make that hydrogen sulfate. You'd get that first product. But if I gave you a prompt and it was 1-to-2, you should probably give me the sulfate product, the ammonium sulfate, where you need 2 ammoniums per sulfate. Okay, Bronsted-Lowry acid classifications. That's really what we were just talking about. They can be monoprotic, like hydrochloric acid. They might only have 1 proton to donate. But they may also be polyprotic. So they could donate many protons. Many being generic, it might be 2, it might be 3, whatever. If it is 2 protons, like that sulfuric acid that I just showed you, then it's called diprotic. Sulfuric acid is a diprotic acid because it has 2 hydrogen ions that can be donated. But it can also be triprotic. It might donate 3 protons. So like I said, we have lots of monoprotic acids, like hydrochloric acid we just talked about, or nitric acid. Those are monoprotic because they only have 1 hydrogen to donate. And you can see that in the formula. We have diprotic acids, like maybe this one. That one's called carbonic acid, but you can see that there are two hydrogens there. So it can donate two different hydrogens. That's a diprotic acid. It's a polyprotic acid, but more specifically, it's diprotic. Or sulfuric acid also could donate those two different protons. You could even have triprotic, like phosphoric acid. So there's three hydrogen ions that can be donated. It's polyprotic, it's triprotic. All good with that? Know what's going on? So how about this thing? That's monoprotic. There are four hydrogen ions there. Can all of those, or four hydrogens, can all of those be donated? No, it's only the one out front that's actually an acidic proton. So you kind of have to look at things carefully sometimes. This is a carboxylic acid, technically, that we'll talk about maybe later, and some of us have talked about it already because we're in a biochem class. But only one of those hydrogen ions is actually able to be donated. So that's a monoprotic acid. How about this one?
No. Can't donate any.
You can donate at least one, become hydroxide. We usually write hydroxide like this, right? Is that second hydrogen ion easily transferred or lost? Probably not if we don't keep it out in front in this context, right? But technically, it could lose that other hydrogen, and then you just end up with that thing. You've seen that before, right? Oxide. Now, like I said, that second proton would be pretty tough to pull away from hydroxide. But you could technically do it. It might actually be considered a diprotic acid, but for our purposes, it's really monoprotic, right? Because we're never going to have it react to turn into oxide.
So H2 is monoprotic.
Yeah, it's, for our purposes, it is technically possible to, but that hydroxide is really, really unlikely to lose another proton. In fact, it's more likely to just gain the proton back and become water. So, although technically it could be a diprotic acid, for our purposes it's probably monoprotic. But you guys kind of understand, there's always exceptions to stuff. But generally speaking, if you see two out front, it's a diprotic acid. This had one, it's just a monoprotic. And then water, who cares? We're not really worried about it that much. It could technically be a diprotic acid, but usually it acts monoprotic. Okay, Lewis acids. A whole nother definition for you to learn. You're probably loving this by now, right? There's a whole different scenario, a different way of looking at this. Lewis acids accept an electron pair. To form a covalent bond. So remember how I told you when you had that free proton in solution, it doesn't stay that way. That is going to react with a water molecule to make hydronium, right? That process of making hydronium, I have a pair of electrons here on this water molecule that is going to be accepted by that hydrogen ion so that I can make a bond between that oxygen and hydrogen ion and have that hydronium ion over here that has that +1 charge overall. So again, this is just kind of a strange context. It's the same thing we were talking about before, just a different way of looking at it. The water donates a pair of electrons that's accepted by this hydrogen to make a covalent bond. But this is the one that gets really weird. Because it doesn't have to be a hydrogen ion that's accepting those pair of electrons. It could be almost anything. Right? So another example, put a few more examples up here to make this make sense at the end of the day. That thing. What was that? Ammonia, NH3. That can react with a hydrogen ion again. Remember we talked about it before as being a Bronsted-Lowry base because it can accept the proton. So when it is accepting a proton, it donates this pair of electrons to make a bond between it and that hydrogen ion. And you end up with this product. A nitrogen bonded to 4 hydrogens. The whole thing has that positive charge. It's somewhere in there. Doesn't really matter where it is. But that's really what was happening. So this is the hydrogen ion here is acting as an acid. That ammonium that's donating the electrons, if you guys were paying attention to the Bronsted-Lowry acid base definitions, the Lewis base definition is just the thing that donates the protons, or donates the pair of electrons to form a covalent bond. So you might want to fill that in real quick. I have a few more examples still. You're fine. It's not that hard.
This is all super simple.
But we had to come up with that definition for a reason. Because it doesn't have to be a hydrogen ion that's donated, turns out.
What?
Or it doesn't have to be a hydrogen ion that accepts that pair of electrons. It could be something else. It could actually be a silver ion. And so this is one of those rare exceptions to the rules. The silver ion is going to end up with covalent bonds. Right? Remember, metals don't usually make covalent bonds, but this is kind of a weird exception. This can actually accept a pair of electrons from something like ammonium so that you end up with a bond. In fact, it wasn't weird enough already. It can actually accept 2 pairs of electrons to make 2 bonds. This would just be another ammonium over here, or ammonia. I'm just going to draw it backwards so that the electron pair was where I could actually work with it a little easier. And you end up with this silver that's bonded to 2 different nitrogens. And you get this weird product. There still would be a positive charge at the end of the day. It's just part of that molecule as a whole now. So that's kind of a weird scenario, right? There was no hydrogen being donated here. This is not a Bronsted-Lowry acid, but that silver is considered a Lewis acid. And the ammonias are considered Lewis bases. And it's similar enough to an acid-base reaction that we consider this an acid-base reaction. Right, this is my acid, these are my bases that are reacting with it. But it's not, it can't be covered under the Arrhenius acid definition. It can't even be covered under the Bronsted-Lowry acid-base definitions. So we had to come up with a whole new acid-base definition to apply to these. Yes.
So is there always going to be hydrogen, like in the equation somewhere, even if it's not being the donated proton?
No. This will be the other scenario. You guys remember boron and how it's kind of weird?
Yeah.
It only makes 3 bonds. Do those 3 bonds satisfy the octet rule for boron? No. How many electrons does it actually have right now? If you count the ones that are shared. It has 6. That's not 8. Right? That's also not 6. So it's got 6. It wants 8, right? So it could actually accept another pair of electrons to be happy. If I have separate here a fluoride ion, that boron can actually accept a pair of electrons from that fluoride ion to make this product down here. A boron that has 4 fluorines attached to it. Again, remember, since that fluoride ion was negative, there's got to be a negative charge somewhere in here, but it doesn't really matter where it is. And I'm being a little bit lazy here. I need to make sure that I have all those dots where they're supposed to be. So again, don't have to have a hydrogen anywhere. This is my acid because it's accepting a pair of electrons. This is my Lewis base because it's donating a pair of electrons. It's just a really weird thing. So I know this definition is probably the hardest of the 3 because these are not even close to the same thing as an Arrhenius acid or Arrhenius base in some cases. So it's weird to lump these in, but the reaction is similar, so they call these acid-base reactions. But again, you could not define this as acid-base under those other definitions. This is definitely not a Bronsted-Lowry acid. This is definitely not an Arrhenius acid, but it is a Lewis acid. So there's a reason for the 3 different definitions. They're just, it all depends on context. Because all these reactions are similar, but not all the same. They can't all be covered by one definition. Still okay? I know, it's really weird. You just gotta accept it to a certain extent. But know when something's a Bronsted-Lowry acid base, know when something's a Lewis acid or base, know when something's an Arrhenius acid or base. Right? Sometimes they're all 3. But sometimes only one definition can cover it, maybe 2 definitions at the best. So you gotta kind of try to understand the difference. Right? Lewis acid-base reactions, obviously you have a formation between covalent bonds between an electron pair donor and acceptor. You already have examples for that. We don't have to do more. The one thing, I was looking in the book, I did forget to do one thing. This goes with the polyprotic acids, and so if you can draw it nearby there, or maybe put it in the margin down below or something like that. With those, I'm just gonna add a new page here. With the polyprotic acids, you guys need to do ionization in stepwise fashion. Say I have, we'll do the most complicated one, just so you guys have something to look at. If I have this acid, it's polyprotic. Specifically, it's what? No, if it's got 3 hydrogens, it's more specific than the poly. It's triprotic. So it can donate 3 different hydrogen ions, right? So I'm going to do that stepwise. You can react with the water here, and you'll end up with this product and this product. Oops. You guys recognize this from before? What's that called? That is dihydrogen phosphate. Almost had it. Dihydrogen phosphate. So you can lose 1 proton to make that dihydrogen phosphate. But then this dihydrogen phosphate can donate a proton to water. and you end up with this product. Now, this product would have what charge? -2, because it's hydrogen phosphate. You have that memorized anyway, right? But do you see why it became -2?
Yeah.
This donated a proton that has a +1 charge. That's why this ended up with a -1 charge here. This thing already has a negative charge. It's going to donate another positive proton and end up with a -2 charge. So they have those charges for a reason. Each successive hydrogen you lose makes it one more negative. If I'd make another hydronium ion over here. And then finally, even that last thing, hydrogen phosphate, can donate a proton to solution. And then you'd get just phosphate at the end. Plus a hydronium ion. Now the reason why we're showing this is because you need to understand that all of these hydronium products contribute to my pH when I put phosphoric acid into a solution, right? It might lose the one, it might lose the second one, it might even lose the third one, and all of those hydrogen ions are going to contribute to my pH and make it drop a little bit more.
Strong acid.
But what you're going to see with most of these things, phosphoric acid is not a strong acid. It's a weak acid. Right, which means I should probably put a reversible arrow there. And that also means that about 99% of it is going to stay in this form. Only about 1% or less than 1% is going to become that dihydrogen phosphate and make hydrogen ion in solution. And this is a weak acid. This is an even weaker acid. This one down here is a weak acid too. The weakest of all three. So when you're looking at this multi-stage ionization, you need to understand that, right, even though there's lots of opportunities to make hydrogen ion, you're really not going to make that much in that solution. You're not necessarily going to make that much. But also from one step to the next, which step's going to make more? This first ionization, the second ionization, this third ionization, which one's going to make more hydrogen ion? The first one, for two different reasons. First off, I told you that this is a weaker acid, the second one's a weaker acid than the first one. So that would be one good reason why there's less. But also, you do understand that before I can lose a proton from this thing, I have to have it at all. And only from that first step do I even make that dihydrogen phosphate so that I could try and lose a second proton. So only 1%, I told you, of my original solution turned into this. So only 1% of that could actually end up as hydrogen phosphate, could end up as hydronium ion, could produce hydronium ion. So what's 1% of 1%? So only like 0.01% of the solution is going to end up contributing to that hydrogen ion there. And then that transfers down here too. If this is only 0.01% of the solution, about how much of it could actually do I need one more zero or not? I had to move it 1, 2. And that would be there. No, I do actually need that extra zero. It'd be 0.0001% of the solution would end up in that form. Alright, so even assuming they were all equivalent as far as what's the strongest and weakest acid, this would have to contribute less down here because there's not very much of this hydrogen phosphate to begin with. Only 0.01% of the original thing is in that form. So each successive stage produces less hydrogen ion. Does that make sense? And that's what you need to worry about at the end of the day. But you need to see those connections, right? The reason why you make the least amount of hydrogen ion in that last stage is you can only get that hydrogen phosphate by ionizing dihydrogen phosphate. And you can only get dihydrogen phosphate by ionizing the phosphoric acid from the get-go. Kind of follow along with that? That's the only extra thing that I forgot to do. So now that you have an example for that, and you know that you get the most hydrogen ion from this first step, not from the other two, these are actually almost negligible, then we're probably going to be okay.